This lecture is dedicated to the structure, main parameters and functions of the injector complex of the accelerator collider NICA. The NICA complex includes several accelerating facilities, such as 2 linear accelerators, 2 cyclic accelerators, 2 storage rings, which are operated in the mode of colliding beams, an experimental facility, and beam transport lines. Operationally, one may emphasize the main units of this accelerator facility: the main synchrotron, which provides beams to experimental facilities and fills the collider, also referred to as the nucleotron, along with 2 independent injection chains. The nucleotron is a facility that provides beams of the required sort with the required parameters and the energy needed for experiments. For the nucleotron to effectively accelerate the required sorts of ions, these ions must enter the nucleotron, that is, by means of an injection. For an injection into the nucleotron, 2 independent injection chains are used: a heavy ion injection chain and a light ion injection chain. Meanwhile, ions emerge in the ion sources and initially get accelerated by the linear accelerator. After that, there may be 1 or more additional cyclic accelerators needed to increase the intensity of an injected beam. Where does the necessity to have 2 injection chains come from? And how do light ions differ from heavy ions? An ion has 2 characteristics: its atomic number, which is equal to the sum of protons and neutrons located in the nucleus of the given element, and the charge number, which is the difference of nuclear charge and the charge of the electrons located in the nuclear shells, all expressed in a value of elementary charge. For example, for light ions, the atomic number amounts from 1 to about 20. For heavy ions, the atomic number is more than 100. There is a certain border region between them, which may be attributed to one or the other type of ion. The definition of the borderline between light and heavy ions is more a technical issue than a problem of some deep physics. What is the fundamental difference between light and heavy ions? For example, the ratio of the charge number to the mass number for the ions of the lightest element in the Mendeleev periodic table, hydrogen, is 1. Its nuclear charge is equal to 1 electron, while its nuclear mass is equal to 1 nucleon. That is why the charge-to-mass ratio is equal to 1. For heavier elements, starting from deuterium, which is a heavy hydrogen isotope, for a bare nucleus stripped of electrons, the charge-to-mass ratio equals 1 to 2. This ratio of 1 to 2 for bare nuclei remains close to carbon nuclei. From the viewpoint of acceleration, at the early stage of beam formation, the charge-to-mass ratio is essential. As a rule, at the initial stage, acceleration is performed by a linear accelerator. To obtain the required kinetic energy per 1 nucleon in the nucleus, it is necessary to create an electric field at a certain intensity. The higher the charge of a nucleus, the lower the intensity of the electric field needed to obtain the given energy. Respectively, this statement may be articulated in a slightly different way. The lower the ion charge, the greater the length of the accelerator needed to obtain the required energy with a given threshold value of the intensity of the electric field. Accordingly, if we accelerate ions with a great ratio of the charge number to the atomic number, for instance, protons, then the linear accelerator may be more compact. If we accelerate heavy nuclei, then the accelerator must be longer and under the same intensity of the accelerating field. But that is only a part of the problem. Obtaining heavy ions of heavy elements in a very high charge state, for example, in the form of completely stripped nuclei, is technically very complicated. Typically, such ions as gold, uranium, or lead ions undergo the initial acceleration stage in the form of partially stripped nuclei, and there are quite a lot of electrons on the orbits around the nucleus. Within the NICA project, for example, it is planned to accelerate gold ions in the charge state of +31. This means there still remains 79 -31 electrons on the orbits around the nucleus. That is, it is not a bare nucleus that is accelerated, but rather a nucleus and a group of electrons located on the orbits around the nucleus. What does it lead to? First, the maximum energy at the nucleotron may be obtained only under the maximum charge-to-mass number ratio. If we accelerate partially stripped ions, we will not get the total projected energy. Second, if the nucleus has electrons on the orbits, then the ion may lose these electrons when interacting with residual gas atoms, and in this case, it falls out of the acceleration mode. To ensure lossless acceleration of heavy ions that have electrons on the nuclear orbits, there are strict requirements for vacuum conditions in the accelerator chamber. When fully stripped nuclei are accelerated, there are no electrons on the orbits, hence the loss channel related to the loss of electrons by the ion is absent. An ion may be lost only due to an electron capture from residual gas atoms. This fundamental difference in the physics of ion properties leads to the necessity to create two injection chains. Meanwhile, the quantity of accelerators double at the early stage of acceleration, but it turns out to be technically justified, because the opposite requirements couldn't be met in one device. The injection chain of the nucleotron within the NICA complex consists of two parts: a light ion injection chain and a heavy ion injection chain. The first one includes a number of light ion sources, such as a laser source, a polarized ion source, and a duoplasmatron. Later on, I'm going to speak about these sources in more detail. They are followed by an RF linear resonant accelerator, from the exit of which the ions enter the nucleotron. For light ions, a linear acceleration is used to accelerate bare nuclei to fully stripped nuclei. That is why the vacuum conditions at the nucleotron are suitable for the lossless acceleration of such ions. The second injection chain includes a larger number of accelerators. It includes a heavy ion source with a sufficiently high charge state, followed by a linear accelerator, which provides enough energy for injection into the intermediate cyclic accelerator. There is also a cyclic accelerator, the so-called booster, designed to provide ion accumulation of the required amount. Its vacuum chamber has good vacuum conditions. It accelerates ions to the energy intensity needed for effective gold ion stripping into fully stripped nuclei. This entire injection chain is located in the existing synchrophasotron building and the buildings attached to it. The injection chain includes two linear accelerators and a cyclic accelerator booster. I'm going to elaborate on the features of each of the injection chains.